The lack of an equipment grounding conductor violates the National Electrical Code requirement for grounding all electrical equipment. The use of the grounded conductor as both the grounding and grounded conductor is a hazardous practice that can result in electric shock or equipment damage. The lack of warning markings on the wire colors for a 480-volt circuit poses a significant electrical hazard. While the state and city may exempt themselves from National Electrical Code jurisdiction, they cannot exempt themselves from the Occupational Safety and Health Act, or OSHA, and other workplace safety regulations. OSHA requires employers to provide a safe workplace and protect employees from electrical hazards. The electrical work described is not in compliance with OSHA's electrical safety standards. Recommended actions include gathering evidence of the electrical safety violations, including photographs and documentation. Discuss concerns with the employer in writing outlining the specific violations and the potential hazards they pose. Request that the employer implement corrective actions to address the safety concerns. If the employer refuses to address the safety concerns, contact OSHA and file a complaint. The concerns about the electrical safety violations are valid. There is a responsibility to ensure a safe workplace. If the employer refuses to address the safety concerns, promptly report them to OSHA. Now let's delve deeper into the specifics of these safety concerns and how they relate to both the National Electrical Code and OSHA regulations. Firstly, the absence of an equipment grounding conductor is a critical violation. According to the National Electrical Code, specifically Article 250, all electrical equipment must be properly grounded. The purpose of an equipment grounding conductor, often a green or bare wire, is to provide a low impedance path for fault current to return to the source. This path allows for the rapid operation of overcurrent protective devices like circuit breakers or fuses, which quickly de-energizes the circuit in the event of a ground fault. Without this conductor, a ground fault can cause the metal enclosure of electrical equipment to become energized, posing a severe shock hazard to anyone who comes into contact with it. In the context of highway lighting, this means that light poles, junction boxes, and other metallic components could become energized without immediately tripping a breaker, creating a dangerous situation for maintenance personnel and the public. Secondly, using the grounded conductor, commonly referred to as the neutral wire, as both the grounding and grounded conductor is a dangerous practice. The National Electrical Code strictly prohibits this in most situations. The grounded conductor is intended to carry current under normal operating conditions, providing a return path for the current flowing through the circuit. Grounding conductors, on the other hand, are intended to carry current only during fault conditions. When the grounded conductor is used for both purposes, it can create a situation where the metal enclosures of equipment are energized with a small voltage, even under normal operating conditions. This is because the grounded conductor is typically connected to the neutral point of the power source, which is usually at or near ground potential. However, due to voltage drop along the conductor and other factors, it may not be exactly at ground potential. This can result in a voltage difference between the enclosure and true ground, creating a shock hazard. In addition, if the grounded conductor becomes disconnected or broken, the metal enclosures of equipment can become energized with the full line voltage, posing a lethal shock hazard. Thirdly, the lack of warning markings on wire colors for a 480-volt circuit is a significant safety concern. The National Electrical Code specifies color coding requirements for electrical conductors to help identify their purpose and voltage level. For example, in a 480-volt system, conductors are often required to be identified with specific colors, such as orange, yellow, and brown. Using different colors or failing to properly mark the wires can create confusion and increase the risk of accidental contact with live conductors. In this case, using a white wire, which is typically reserved for grounded conductors in 120-volt circuits to carry 480 volts, poses a significant hazard. Anyone working on the system who assumes that the white wire is at or near ground potential could receive a severe electrical shock. Now, let's consider the legal aspects of this situation. Even though the state and city may have exempted themselves from National Electrical Code jurisdiction, they cannot exempt themselves from OSHA regulations. OSHA is a federal agency that is responsible for ensuring safe and healthful working conditions for employees. OSHA has specific electrical safety standards that employers must follow to protect their employees from electrical hazards. These standards cover a wide range of topics, including grounding, wiring methods, personal protective equipment, and training. The electrical work described is not in compliance with OSHA's electrical safety standards, particularly those related to grounding and wiring methods. OSHA requires employers to provide a workplace free from recognized hazards that are causing or are likely to cause death or serious physical harm to employees. Failure to comply with OSHA regulations can result in significant fines and penalties. Furthermore, if an employee is injured or killed as a result of an electrical safety violation, the employer may be subject to criminal charges. Given these safety and legal considerations, it is imperative to take action to address these issues. The first step is to gather evidence of the electrical safety violations. This includes taking photographs of the wiring methods, grounding connections, and any other areas of concern. It is also important to document any specific instances where the lack of proper grounding or wiring methods has created a hazard. This documentation will be crucial in supporting claims if it becomes necessary to file a complaint with OSHA. Next, it is important to discuss concerns with the employer in writing. This provides a formal record of the concerns and demonstrates commitment to resolving the issues. In the written communication, outline the specific violations and the potential hazards they pose. Cite relevant sections of the National Electrical Code and OSHA regulations to support the claims. Request that the employer implement corrective actions to address the safety concerns. This could include hiring a qualified electrical contractor to inspect and repair the electrical system, providing additional training to employees on electrical safety, and implementing a written electrical safety program. If the employer refuses to address the safety concerns, it is important to contact OSHA and file a complaint. OSHA has the authority to inspect workplaces and issue citations for violations of its regulations. If OSHA finds that an employer has violated its electrical safety standards, it can order the employer to correct the violations and assess penalties. When filing a complaint with OSHA, provide as much detail as possible about the violations, including photographs, documentation, and the names of any witnesses. OSHA will typically investigate the complaint and take appropriate action. In addition to contacting OSHA, it may also be helpful to seek legal advice from an attorney who specializes in workplace safety. An attorney can advise on legal rights and options, and can represent in any legal proceedings. To further understand the complexities of electrical safety, let's explore some additional resources. The OSHA website provides a wealth of information on electrical safety standards, including fact sheets, training materials, and enforcement guidance. The National Electrical Code is a comprehensive set of standards for the safe installation of electrical wiring and equipment. It is updated every 3 years and is widely adopted by states and municipalities throughout the United States. The Oklahoma Electrical Safety Laws provide specific regulations related to electrical work in the state of Oklahoma. It is important to familiarize with these laws to ensure compliance. The National Fire Protection Association, or NFPA, offers various resources related to electrical safety, including training courses, publications, and standards. Understanding grounding and bonding in detail. Grounding and bonding are two critical concepts in electrical safety, and it's essential to understand their individual roles and how they work together to protect people and equipment. Grounding refers to connecting electrical equipment and systems to the earth. This connection provides a low impedance path for fault current to flow back to the source, allowing overcurrent protective devices to quickly clear the fault. The primary purpose of grounding is to minimize the risk of electric shock by ensuring that metal enclosures and other conductive parts of electrical equipment are at or near ground potential. There are two main types of grounding systems: equipment grounding and system grounding. Equipment grounding involves connecting the non-current carrying metal parts of electrical equipment, such as enclosures, raceways, and frames, to the grounding electrode system. This creates a low impedance path for fault current to flow back to the source, tripping a circuit breaker or fuse and de-energizing the circuit. System grounding, on the other hand, involves grounding the neutral point of the electrical supply system, such as the transformer or generator. This helps to stabilize the voltage of the system and provide a reference point for fault detection. Bonding, in contrast, refers to connecting different metal parts of an electrical system together to create an electrically conductive path. The purpose of bonding is to minimize voltage differences between different metal parts, reducing the risk of electric shock. Bonding is typically accomplished by using bonding jumpers, which are short lengths of wire or metal straps that connect different metal parts together. Bonding is particularly important in areas where there are multiple metal parts in close proximity, such as in a metal enclosure or raceway. By bonding these parts together, any voltage differences that may exist between them are minimized, reducing the risk of electric shock. The NEC provides detailed requirements for grounding and bonding in Article 250. This article covers a wide range of topics, including the selection and installation of grounding electrodes, the sizing of grounding and bonding conductors, and the bonding of metal enclosures and raceways. Understanding overcurrent protection. Overcurrent protection is another essential aspect of electrical safety. Overcurrent is any current that exceeds the rated current of a conductor or device. Overcurrent can be caused by a variety of factors, including short circuits, ground faults, and overloads. Short circuits occur when there is an unintended connection between two or more conductors of different potential. This results in a large surge of current that can quickly damage equipment and cause a fire. Ground faults occur when there is an unintended connection between a conductor and ground. This can also result in a large surge of current, particularly if there is not a properly installed equipment grounding conductor. Overloads occur when a circuit is subjected to more current than it is designed to handle. This can cause the conductors and equipment to overheat, leading to damage and potentially a fire. Overcurrent protective devices are designed to automatically interrupt the flow of current in the circuit when an overcurrent condition occurs. The most common types of overcurrent protective devices are circuit breakers and fuses. Circuit breakers are electromechanical devices that trip and open a circuit when an overcurrent is detected. They can be reset and reused after the overcurrent condition has been cleared. Fuses are one-time use devices that melt and open a circuit when an overcurrent is detected. They must be replaced after they have been blown. The NEC provides detailed requirements for overcurrent protection in Article 240. This article covers a wide range of topics, including the selection and sizing of overcurrent protective devices, the coordination of overcurrent protection, and the protection of specific types of equipment. Understanding wiring methods. Wiring methods refer to the way in which electrical conductors are installed and protected. There are a variety of wiring methods available, each with its own advantages and disadvantages. Some of the most common wiring methods include conduit, cable, and wireway. Conduit is a rigid or flexible metal or plastic tubing that is used to enclose and protect electrical conductors. Conduit provides excellent mechanical protection for conductors and is often used in areas where conductors are exposed to physical damage. Cable is a factory-assembled group of conductors that are enclosed in a non-metallic sheath. Cable is relatively easy to install and is often used in residential and commercial buildings. Wireway is a metal trough or channel that is used to support and protect electrical conductors. Wireway is often used in industrial settings where there are a large number of conductors. The NEC provides detailed requirements for wiring methods in Chapter 3. This chapter covers a wide range of topics, including the selection and installation of wiring methods, the support and protection of conductors, and the grounding and bonding of wiring systems. It is crucial to select the appropriate wiring method for each application and to ensure that it is installed in accordance with the NEC requirements. Understanding personal protective equipment. Personal protective equipment, or PPE, is equipment that is worn by workers to protect them from hazards in the workplace. In the electrical industry, PPE is essential for protecting workers from electric shock, arc flash, and other electrical hazards. Some of the most common types of PPE used in the electrical industry include rubber insulating gloves, rubber insulating sleeves, arc-rated clothing, and safety glasses. Rubber insulating gloves are used to protect workers from electric shock when working on energized equipment. They are available in different voltage ratings and must be inspected and tested regularly to ensure that they are in good condition. Rubber insulating sleeves are used in conjunction with rubber insulating gloves to protect the arms from electric shock. Arc-rated clothing is designed to protect workers from the intense heat and energy produced by an arc flash. It is typically made from flame-resistant materials and is rated according to its ability to withstand an arc flash. Safety glasses are used to protect the eyes from flying debris, sparks, and other hazards. OSHA requires employers to provide PPE to employees who are exposed to electrical hazards and to ensure that employees use the PPE properly. It is crucial to select the appropriate PPE for each task and to ensure that it is in good condition and properly maintained. Understanding lockout-tagout procedures. Lockout-tagout, or LOTO, procedures are used to prevent the accidental energization of equipment during maintenance or repair. LOTO procedures involve isolating the equipment from its energy source and applying a lock and tag to the energy isolation device. The lock prevents the energy isolation device from being turned on, and the tag provides information about why the equipment is locked out and who is responsible for the lockout. LOTO procedures are essential for protecting workers from electrical shock, arc flash, and other hazards that can occur when equipment is accidentally energized. OSHA has specific requirements for LOTO procedures in its Control of Hazardous Energy standard. This standard requires employers to develop and implement a written LOTO program to train employees on LOTO procedures and to ensure that LOTO procedures are followed correctly. It is crucial to follow LOTO procedures whenever working on electrical equipment to prevent accidental energization and to protect workers from hazards. Addressing specific concerns in highway lighting. Let's address the specific concerns raised in the context of highway lighting. The use of underground polyvinyl chloride, or PVC, conduit is a common practice for underground electrical installations. PVC conduit is non-conductive and provides excellent protection for conductors from moisture, corrosion, and physical damage. However, because PVC conduit is non-conductive, it does not provide a ground fault path. This means that if a conductor inside the PVC conduit develops a ground fault, the fault current will not be able to return to the source through the conduit. This is why it is essential to install a separate equipment grounding conductor inside the PVC conduit to provide a ground fault path. The use of seal-tight, or flexible metal conduit to turn 90 degrees is also a common practice. Seal-tight provides flexibility and allows for easy routing of conductors around obstacles. However, seal-tight may not always provide a reliable ground fault path, particularly if it is not properly installed or if it becomes damaged. Therefore, it is important to ensure that seal-tight is properly bonded to the equipment grounding system. Bonding can be achieved by using bonding jumpers to connect the seal-tight to the metal enclosures of the equipment. In the specific case described, the lack of an equipment grounding conductor in the PVC conduit and the reliance on the grounded conductor as both the grounding and grounded conductor creates a significant safety hazard. If a conductor inside the PVC conduit develops a ground fault, the fault current will have to return to the source through the grounded conductor. This can cause the metal enclosures of the light fixtures to become energized, posing a shock hazard to anyone who comes into contact with them. In addition, if the grounded conductor becomes disconnected or broken, the metal enclosures of the light fixtures can become energized with a full line voltage, posing a lethal shock hazard. To address these concerns, it is essential to install a separate equipment grounding conductor inside the PVC conduit and to ensure that all metal parts of the electrical system are properly bonded together. It is also important to use the correct wire colors to identify the different conductors and to provide warning markings to indicate the voltage level. The use of a white wire to carry 480 volts is a clear violation of the NEC and creates a significant safety hazard. Additional considerations for non-licensed and inexperienced workers. The concerns are further amplified by the fact that the individuals who will be working on the electrical system are non-licensed and inexperienced. Non-licensed and inexperienced workers may not have the knowledge and skills necessary to identify and avoid electrical hazards. They may also be more likely to make mistakes that can lead to electrical shock, arc flash, or other injuries. It is essential to provide adequate training to non-licensed and inexperienced workers on electrical safety. This training should cover topics such as basic electrical theory, grounding and bonding, overcurrent protection, wiring methods, personal protective equipment, and lockout-tagout procedures. The training should also be hands-on and provide workers with the opportunity to practice the skills they have learned. In addition to providing training, it is important to supervise non-licensed and inexperienced workers closely and to ensure that they are following safe work practices. This may involve providing them with detailed instructions, monitoring their work, and correcting any unsafe behaviors. It is also important to create a culture of safety in the workplace where workers are encouraged to report hazards and to ask questions if they are unsure about something. Ultimately, ensuring electrical safety in highway lighting and traffic control systems requires a comprehensive approach that includes compliance with the NEC and OSHA regulations, proper grounding and bonding, overcurrent protection, appropriate wiring methods, the use of personal protective equipment, lockout-tagout procedures, and adequate training and supervision of workers. By taking these steps, it is possible to create a safe working environment for everyone involved and to prevent electrical accidents and injuries.